analogy that you made with the prism, changing the spot and green light on the wall makes perfect sense, but I wondered if you could elaborate a little bit on the two types of diffraction you were looking at. You said you use small angle scattering and then also something else that I didn't...
The two geometries. So there was grazing incidence,
Grazing incidence, and then what was
and specular.
Specular, yeah. Could you explain those?
Yes. By the way, Sarah and I spent many, many long nights measuring these devices. She was my electrical engineer expert. Okay. So this requires a little bit of background in X-ray diffraction, but if you're looking at reciprocal space, you have something called an Ewald sphere, and it will interact with your orientation sphere, how your rods are aligned. The diameter of this is inversely proportional to the crystallographic spacing that you're measuring. And so if you only have it in one orientation, you can look at nanorods that are anywhere between horizontal and this angle. But you can't see the nanorods that are standing perpendicular. So this is in the grazing incidence geometry, and the reason it's grazing incidence is because it's literally coming in almost parallel to the film. But in order to get high resolution of the peak, it's going to show all the nanorods standing up, which we really need. Then we tilt it by this angle, theta d, into the specular condition. Sarah?
Okay. So I wonder, you mentioned the high chalcocite being because the copper atoms are sort of in an amorphous phase that you expect that will give a lower electron mobility. Mm-hmm. Have people done electrical tests on that? I mean, have people compared the electrical performance of low and high chalcocite?
People have made solar cells and heated them up and watched the performance. So that's coupled, they've watched the photocurrent as a function of temperature, and they can see the phase transition happen, but that's combining the optical and the electrical properties. So it's not really getting exactly at the mobility. There haven't been a lot of really good studies on copper sulfide in general, and the reason for that is because it doesn't like to be stoichiometric. We're able to get it to be stoichiometric using our ion exchange technique, but it loves to lose copper ions and become copper deficient. And as you start to become copper deficient, the phase diagram, you move to a different part of the phase diagram that has totally different behavior. So there have been reports in the literature.
I see, but it's hard to isolate that.
Well, this doesn't show the whole space. This is very narrow. But as you move around, you've got this very complex phase diagram as you change your stoichiometry and become copper deficient. And people have a very difficult time measuring whether or not they're actually stoichiometric or if they're 3% deficient, which makes the properties dramatically different.
So you mentioned the challenge of the insulating ligands on the caps of your nanorods. So if you had more time on your PhD, what would you do and what would you not do to remove those ligands?
Well, I've tried the things that I thought would be easiest, because I would have loved to finish this talk with a demonstration of a 10% efficient device. So I tried doing a ligand exchange before aligning them to a shorter ligand, and it was really difficult to get alignment. This self-assembly is extremely dependent upon which ligands you're using, and the surface techniques just aren't available yet to be able to quantify that in a way that could allow us to do good work on that. So I wasn't easily able to exchange the ligands, and I wasn't able to quantify what I was doing before assembly. After assembly, I would also take these films and dip them in a different ligand, hoping that that ligand would exchange out. And what happened was that if the ligand that I dipped it in was very short, then the nanorods, which are 4 nanometers in diameter with 2 nanometer rods, so we've got like a 50% aerial coverage, if you shrink those ligands, then all the nanorods lean a little bit, and it looks like grass that someone had a picnic on. You can see that there was some sort of order, and it makes nice patterns, but they all lean over quite a bit. So I wasn't able to exchange the ligands afterwards to something shorter. And if I exchange it to something longer, well, that's also insulating. So those are the things that I wouldn't do. The things I would do would probably focus on 2 things. One, a better alignment technique that allows you to have ligands that are very short. And so maybe that would be an amphiphilic particle where half of the rods were a very, very short but polar molecule and half were nonpolar. That could get that perfect assembly, and maybe you could do that with short rods. So it would involve a very different alignment technique than what I was using. Or you could use electrophoretic assembly, which doesn't require long ligands. Alternatively, you might want to think about exchanging the ligands to inorganic ligands, because inorganics might have higher conductivity, and so you could keep them long. So Dmitry Tilapin recently showed some really impressive inorganic ligands. You could make those longer.
So you had one plot showing aspect ratios and changes in performance, I think, in terms of the length of the nanorod and the diameter. And I was just curious relative to this last comment that you made. I mean, maybe it would be okay if they leaned, but they were a little more efficient in a sense. I mean, what about a trade-off between efficiency in terms of the solar, I mean, the photovoltaic effect versus the concern you have with your ligands? And in terms of rod shapes, I mean, how do all these pieces fit together? It seems like there's got to be sort of a sweet spot where all of these pieces are just about right.
Are you asking what angle the rod, what angle can we afford to have it lean at?
Yeah, for example, you mentioned that the ligands were shorter, which maybe improved conductivity a bit. They would lean a little bit more. I mean, so there would be a trade-off between how much you lose when they're not straight versus how close they are.
Yeah. So if the rods lean at 20 degrees, we lose 4 nanometers in the thickness of our film, which isn't that much. It starts off as 30 nanometers, so it's pretty small to begin with. But a lean of 20 degrees is very acceptable and not so noticeable to the film. Once we get past 20 degrees, it's going to start decreasing the thickness of the film pretty quickly. And this is already a concern. We would need to have pretty extensive light trapping in a system that's 30 nanometers thick to begin with, but if we get it down to 10 nanometers thick or something, we'll have a problem.
And then the aspect ratio, I mean, are longer rods better typically, or shorter rods better? Your film is proper thickness?
So longer rods are certainly better for making the film thicker, and we used the longest rod that we were able to reliably get to stand up. And so those were somewhere between 30 and 40 nanometers long. As we got to longer rods, we weren't able to find a set of conditions that allowed them to kinetically reach the place they needed to get. So in order to align, we need them to be pretty concentrated in solution. That induces the liquid crystal phase transition. But if they're really long and then they're also concentrated, kinetically it's really difficult. They're interfering with each other. So we were kind of left at 40 nanometer length.
So in the last question, I mean, if these things are, I mean, doing very simple math, if these things are 10% efficient, that means 90% inefficiency, there's going to be a lot of heat. How long will these things operate when it gets really hot? I mean, a lot of the things you're showing have temperature differences of just, tens of degrees of whatever. We don't use much Kelvin in mechanical engineering, but tens of degrees. But I mean, how are these things expected to perform in kind of an operating environment with big temperature differences?
So photovoltaic cells can get up to 50 degrees Celsius in the field. And so using very tiny copper sulfide nanocrystals, we would have a problem. Our electrical performance would be degraded for sure. Other than that, the ligands, the organic ligands, are stable at 50 degrees Celsius, so it's okay to heat them up that hot. And the crystals themselves are stable for more than hundreds of degrees before they melt. So as long as we're using nanocrystals that are greater than 5 nanometers in diameter, we're in a comfortable regime for the operating temperatures of solar cells. All right, thank you.
Good.